Number 10, solve the system where A is 1, 2, -1, 4. So this is the system of matrix system x prime is equal to A times x, where A is our coefficient matrix. And we're going to solve it using eigenvalues. To find eigenvalues, you want to solve the determinant equation. The determinant of A minus lambda I is equal to 0. So the determinant A minus lambda I is a determinant that cancels, that subtracts lambda across the diagonal. So across the diagonal, here you're going to get 1 minus lambda. In the lower right, you get 4 minus lambda. And then to calculate the determinant, you multiply 1 minus lambda times 4 minus lambda, and then you subtract off 2 times -1. And then multiplying out 1 minus lambda times 4 minus lambda, you get lambda squared. You're going to get a -1 lambda and a -4 lambda. Those combine to give you -5 lambda. And then you have 4 plus 2, which gives you 6. So lambda squared minus 5 lambda plus 6 can be factored into lambda minus 2 times lambda minus 3. And when that's equal to 0, it tells you lambda is 2 or lambda is equal to 3. So we have 2 eigenvalues, which is what we want for a 2 by 2 system. With each eigenvalue, we can find an eigenvector by substituting in the lambda and solving A minus lambda I times k, where k is a column vector, is equal to 0, where 0 is a 0 vector. So A minus 2i is going to subtract 2 across the diagonals. So 1 minus 2 gives you -1, and then 4 take away 2 gives you 2. Notice that these rows are the same. So when you multiply out the first row by this column vector, you get -1k1 plus 2k2 equals 0. And when you multiply the second row, you get exactly the same thing. So what we want is values for k1 and k2 that make this equation true. Your values could be different than mine. I tend to try and stay away from fractions. I tend to try and stay away from negative numbers as much as I can. So solving for k1, I get k1 is 2 times k2, which means I can let my vector k equal, let's see, if k2 is 1, then k1 is 2 times 1, or 2. And I get a solution by multiplying the eigenvector times e to the lambda t. In this case, lambda is 2. So one solution is the vector 2, 1, e to the 2t. Okay, we're going to do exactly the same thing with lambda equals 3. Subtract 3 across the diagonal. To get here, 1 minus 3 is -2. 4 take away 3 is 1. Notice that these aren't identical, but they are multiples of each other. If you take the bottom row and multiply it by 2, you get the upper row. So the equations that would be formed by multiplying each row by this column are going to be equivalent. So I'm going to take the simpler equation, -1k1 plus k2 equals 0. Solve for k1 to get k1 equals k2. And I'm going to let my eigenvector be 1, 1. And so my second solution is 1, 1 e to the 3t. So the solution to the system is C1 times your first solution plus C2 times your second solution. And this should just be an x, not an x squared. It should just be x, or not a subscript. It should just be x. So if you take this and rewrite it in equation form, it looks like this. X of t is 2c1 e to the 2t plus c2 e to the 3t, and y of t is c1 e to the 2t plus c2 e to the 3t. So either way is fine for writing the answer.